Hello, everyone. I hope you're all healthy and well. Welcome to the next talk in our Golden Webinars in Astrophysics series. Our speaker today is Paul Heunigen-Hühne, who is a professor of philosophy at the Leibniz Universität Hannover and the Universität Zürich. My name is Thomas Prusia, and together with Evelyn Johnston, we have again organized today's webinar for you. As in previous webinars, we have arranged for simultaneous language interpretation by Mr. Patricio González, who will be simultaneously translating for us into Spanish. En sus dispositivos pueden escuchar la interpretación al español de la conferencia al pinchar el botón de interpretación que se encuentra en la parte inferior derecha de la ventana Zoom y seleccionar español. We would like to acknowledge the generous support of the Center for Astrophysics and Related Technologies, also known as CATA for its Spanish acronym, to make this webinar series possible.
Thank you all so much for your feedback and comments. If you're watching a recording of this talk on YouTube, please leave your questions and comments below, and please share these talks with your friends and colleagues. If you would like to support the Golden Webinar series or give us feedback, please send us an email. If you're watching this talk on the YouTube live stream and would like to hear the Spanish soundtrack, we invite you to switch over to the Zoom webinar, and you can find the registration link in the description below the YouTube video. And if you have any questions during the live talk, please type them into the Q&A window. You can also upvote questions and comment on them, and we will select the best questions for the discussion after the talk.
Before we begin, as usual, we would like to briefly introduce our other panel members that are with us today. So, of course, Paul, our speaker, Patricio, our interpreter, Evelyn, and myself. Then we have from the Faculty of the Institute of Astrophysics of Pontificia Universidad Católica, my colleague, Manuela Zoccali. We have our postdoctoral fellow, also at the Institute of Astrophysics, Giacomo Venturi. And it is also a great pleasure to welcome our guest panelists with us today. Rohan Radgawankar, who is a recent graduate student at the University of Toledo and an intern at the moment at the Gemini Observatory. We have also Barbara Silva with us today, who is a science historian at the Universidad Alberto Hurtado, who specializes on the modern science history of Chile and Latin America and its global perspective. Also with us today is Daniel Farsani, who is a behavioral scientist with degrees in mathematics and educational science, and an expert of the nature of interactions, both verbal and non-verbal communication in various settings. Most recently, he also worked on analyzing teachers' and students' interactions as a way to promote student attainment in STEM fields. We also have the great pleasure to welcome again on the panel James Peebles, who is the Albert Einstein Professor of Science at Princeton University and the 2019 Nobel Laureate in Physics. We have also with us today Leopoldo Infante, the director of Las Campanas Observatory, Miguel Roth, the Chilean representative of the Giant Magellan Telescope project, Dietrich Bade, who's an astronomer at the European Southern Observatory in Garching, and Ivo Saviano, who's an astronomer and the site manager of the European Southern Observatory of La Silla. And finally, we have our excellent team of Q&A managers who will be working in the background for us, looking through the comments and questions and sorting them: Ricardo Acevedo, Daniela Fernandez, and Carol Rojas.
It is our pleasure to introduce Paul Heunigen-Hühne as our speaker today. Paul completed his undergraduate degree in theoretical physics at the University of Munich in 1971, and then studied for his PhD in theoretical physics at the University of Zurich, which he completed in 1975. Following his PhD, he had a position as a teaching and research assistant at the University of Zurich, and later he was a lecturer in the philosophy of science at the University of Zurich, the University of Bern, and at the ETH in Zurich. In 1990, he was appointed the Professor for Foundational Theory and History of Sciences, especially the exact sciences, at the Institute of Philosophy and at the University of Constance in Germany. In 1997, he became a professor of the ethics of science and the founding director of the Center of Philosophy and Ethics of Science at the Universidad Hannover in Germany. Since 2011, he has been a professor for theoretical philosophy at the Leibniz Universidad in Hanover. And in addition to these appointments, he has held various positions as visiting professor in Switzerland, Yugoslavia, Denmark, and Norway.
Paul's work has focused on issues in general philosophy of science, particularly on the philosophical writings of Thomas Kuhn and Paul Feyerabend, and the subject of incommensurability, which is when scientific concepts are described using languages that do not overlap sufficiently to permit scientists to directly compare the theories. His most recent book, Systematicity, The Nature of Science, is devoted to the question of the nature of science, including the social sciences and humanities, and develops the thesis that scientific knowledge is primarily distinguished from other forms of knowledge by being more systematic. Today, Paul has joined us to tell us what makes science special and why science is so reliable. Paul, we are all ears.
Thank you very much. It's a very great pleasure and honor that you invited me to give a golden webinar in astrophysics, knowing that I'm a philosopher and you're running a high risk. You take that risk because I'm going to tell you what makes science special and why is science so reliable. So I first give you an outline of what I'm doing here, and the outline is this. I'll first treat the question, what makes science special? And then I answer this question, and then I give you a justification of the answer in 9 steps. Then I will make a quick comparison with other positions, and finally I have a summary. So some of you will be completely shocked when you see that. First of all, because a German professor's talk has a structure. You probably never experienced that. And the second thing is that you find here a justification of the answer in 9 steps. And this, of course, contradicts the common use of the word philosophy in the sciences. So I remember Professor Peebles' talk when he said Einstein reached the idea of a homogeneity of the universe in a philosophical way. And what he meant is, more bluntly, this was pure speculation, no data, nothing serious, just an idea. But when Einstein just has an idea about something deep, it's got to be philosophical. So this is really different in professional philosophy, because in professional philosophy, we are really trying to ask questions, sensible questions, give articulate answers, and then argue for these answers. So it's very rational in the same way you are supposed to know from the sciences. Okay, that's the program. Let's see what I can make of it. All right, first I'll give you historical answers on this question, what makes science special, in 4 phases. This is very schematic, but it shows you how we got to the situation we are in today. And that, of course, started like everything almost intellectual, started in antiquity with the Greeks. And in antiquity until the 17th century, scientific knowledge was seen as certain knowledge, and that certainty was established by proof. The paradigm case you may remember from high school is Euclidean geometry. Euclidean geometry is the science of real space, and it somehow gets to axioms, and then you establish theorems by proof, and that's the paradigm case for the idea of science in general. Now, in the second phase, from the 17th century on until the second half of the 19th century, roughly, the arsenal of methods was increased, widened, by having something which was then called the scientific method, and that did not only encompass proofs, but also inductive methods. But the main idea was that the scientific knowledge that is established is also certain knowledge. Now, in the third phase, that lasts until the last third of the 20th century, roughly, that idea that scientific knowledge is certain knowledge eroded. And it eroded to the degree that people now, most scientists believe that scientific knowledge is fallible knowledge. That means knowledge that may be revised in some future time. It's still established by the scientific method in this third phase, but then in the fourth phase, in the last third of the century until now, it's the dissolution of the persuasion that science is indeed governed by the scientific method in the sense of strict rules. The result was gained by historical studies when people really tried to identify this scientific method as strict rules, and it turned out you couldn't find them. And there are also systematic arguments why it's not very plausible that something like a scientific method in that sense exists. So the driving forces of that change of our ideas, what the nature of science is, are two. First, the sciences themselves develop using new methods, becoming more sophisticated, etc. So the subject matter of the question, what makes science special, changes. And therefore, of course, the answers have to change. In addition, it's also the reflection on the sciences develops, and it's also becoming more sophisticated. It's especially our understanding of logics and inductive procedures and all of that. So these two factors together lead to this historical development of our answers, what makes science special. I give you here a chart of these historical answers, which shows you the sort of tragedy in which it results. So we start with deductive proof as the main methodological thing, and that leads to certainty. And from the early 1600s on, then it's seen as a scientific method, in addition to deductive proof, of course, then inductive methods, and that leads then up to the late 19th century. And then the certainty is from the late 19th century on. It's replaced by fallibility. And now if you look, we are here now. So what's left? Just fallibility. Fallibility meaning, in principle, revisability of science, and nothing is certain, nothing is just watertight and forever. So given that historical development, we are at an impasse today. We are left with fallibility, which certainly does not make science special, because all our knowledge is fallible in all areas. So science doesn't seem to be special, and that is not highly plausible. Therefore, what we need is a new answer regarding what makes science special. And this is the journey in which I hope you accompany me here. All right, a few preliminary notes before I start then with the main thesis. In the general theory that I'm presenting, the social sciences, the humanities, mathematics, and the engineering sciences are also included, but I'm not stressing them here because you are a different audience, and I stick to the natural sciences mainly. I will concentrate on them. I will contrast science with other kinds of legitimate knowledge, mainly everyday knowledge. And this sort of contrast is somehow novel because in the history of philosophy in the 20th century, massively influenced by Popper, the main contrast was pseudoscience or metaphysics, so forms of knowledge that were not seen as legitimate. The difficulty of that approach, the Popperian approach, is that you may get the difference between legitimate science and illegitimate knowledge, but what you won't get is the specifics among the legitimate knowledge forms that science have in comparison to, for instance, everyday knowledge and other legitimate forms. And finally, this is only a side remark, because for astronomers, this is not very important. Don't expect sharp boundaries around science everywhere, especially regarding research and developments. There is really a transitory area. We know that from fusion science, for instance, fusion research from the 1940s on, there was the development of a reactor, but at the same time, it was the fundamental basic research concerning plasma physics. You find that also in earthquake engineering, which is, by the way, not the engineering of earthquakes, but it's rather the engineering of structures of buildings that are earthquake resistant. And here's a very sweet discipline, chocolate science, of which you are probably not aware, but it's a real science. The Royal Society of Chemistry from England has edited a book on it. So, and also there you have this transition between fundamental research and development, product development. Anyway, so here is now the answer to what makes science special. And I will explicate that and defend them later. Scientific knowledge differs from other kinds of knowledge, from everyday knowledge in particular, by being more systematic. So that will accompany us through the whole talk. It's more systematic. Now, I shall give you some qualifications of that answer. There are many more. I just give you the most important ones. And here's the thesis again. And the first one is that this higher systematicity concerns not only science as a whole, but it concerns 9 different separate aspects of science, or I call them also dimensions of science. So for instance, that general thesis has to be broken down to, for instance, scientific descriptions. So the thesis is scientific descriptions are more systematic than descriptions in other parts of knowledge. Scientific explanations are more systematic, and so on. I will later go through all these 9 dimensions or 9 aspects. So it's more complicated, it's more structured than just one big thesis. What you see if you read that thesis again, the answer is comparative in character. So scientific knowledge is more systematic. That implies that the other kinds of knowledge need not be entirely unsystematic. So for instance, counting the numbers of pupils, so that some of you who have many children, of course, are always under pressure to. It's very systematic. You count them 1, 3, 5, and that doesn't give you a degree in mathematics because it's a systematic procedure of our everyday knowledge gaining. And finally, it's a remark also probably not entirely relevant here, necessary, more systematic, refers to knowledge about the same domain. If you compare knowledge from different domains, then it's not necessarily that scientific knowledge is more systematic, but about the same domain, then the scientific knowledge is more systematic, that's the thesis, than other parts of knowledge. All right, and then we have something more. In general, being systematic means to embody some sort of order. This is a not very far-reaching definition. It's very hard to say exactly what systematicity means. And in our context, the meaning of systematicity is in fact slightly dimension dependent. So what systematicity means with respect to descriptions is not exactly the same what it means with respect to explanations or the other dimensions. And in addition, it's getting even more complicated. The meaning of systematicity is also discipline and subdiscipline dependent. So when you speak about the systematicity of a description in mathematics, you do not mean exactly the same when you speak about the systematicity of the description of an experiment, for instance. The same with disciplines and subdisciplines, and that makes the whole thing a little complicated, and we'll come to that complication in a minute. A philosophical note for those who are interested: the relationship among these different concepts of systematicity is one of family resemblance, a term by philosopher Ludwig Wittgenstein, but that has no consequence for us here. Now, the point is, this systematicity theory has to be justified. I have to argue for that theory, namely that this main answer is indeed true. And the justification of the answer must show that all sciences are more systematic than other kinds of knowledge in all 9 dimensions. So I'm speaking about a lot of things at the same time. That's not the only problem. The main problem is nobody today has an overview over all scientific disciplines and subdisciplines. Not even their number is known. Because unlike astrography or astrometry or geography, the analog scientography does not exist today as a developed disciplines. That was different 200 years ago, and there are now attempts to do that by artificial intelligence and communication pattern and so on and so forth. But there is just no book that tells you, these are all the sciences and these are all the subdisciplines. And even the number is clear, and the number we can only give orders of magnitude. There's something like 500 disciplines and something like 10,000 subdisciplines, which means if I want to argue every subdiscipline in 9 dimensions, you can calculate it. It's a very large number of theses I have to defend here. All right, and I can't do that. In order to argue the higher degree of systematicity in the 9 dimensions step by step, I will use examples, and I will very often use examples from astronomy, astrophysics, and cosmology. So basically what I'm finally descending, the force of the argument will be that really astronomy, astrophysics, and cosmology is really science because it's so systematic in all 9 dimensions. All right, so the justification of the answer in 9 steps, and I start now going through the different dimensions, and I start with the systematicity of descriptions. So if you look at mathematics, the classical formal sciences, the systematicity of the description is an axiomatic description of the domain of inquiry. So for instance, if you're interested in natural numbers, in everyday life, someone says, well, this is 1, 2, 3, and so forth, whatever that means. And in mathematics, you say, well, you write down the Peano axioms, and then you have all you can know about natural numbers. So very important in the empirical sciences, but also partly in mathematics, is classification and taxonomy. It's extremely relevant in all disciplines. And I mean, earlier it was thought that, you know, if you do botany, you just classify plants, and that's utterly boring. That's a deep misunderstanding, and I'll show you exactly why in a moment. So, for instance, if you count biological species or classify biological species, we speak about 8 to 11 millions. If we speak about chemical substances and sequences, at the moment, we have something like 235 millions, plus 15,000 each day, probably also on Sundays. Then chemical reactions, it's something like 129 millions. Diseases, of course, you know, the catalog. Language is something like 7,000. So these seem to be enormously large numbers at which you astronomers can only smile, as you see in a moment. So if you look at the example of astronomy and the classifications and taxonomy, which are historically variable, and sometimes controversial, as you possibly know. So, for instance, classifications of stars into O, B, A, F, G, K, M. That's an old classification. Then the variable stars are classified, the galaxies are classified, quasars are classified. Now, classifications is not just for people who are neurotically orderly, you know, who wouldn't have anything orderly somehow. It's extremely important for science, and I'll tell you in a moment why. First, we have a huge number of objects. And second, adequate classifications is presupposition of another fundamental means of systematic description. And I come to that now. And that is the following, that in the sciences, we love phenomenological laws. That is, empirical regularities, for instance, like Hubble's law, the velocity of a galaxy is h0 times the distance. But look, you see that very clearly here. This law only works if you have first sorted out the galaxies. If you have different celestial bodies here, you will never find this law. So only if you have the correct classification, then you can find the law. And that you see in many scientific disciplines, the correct classifications are presupposed by the possibility of finding empirical regularities. And of course, the importance of something like that, or the ideal gas law, and so on and so forth, they all presuppose adequate classification. Now, the analog of classification in time is periodization. You have a certain development, and you distinguish different phases of the development. Exactly what I did, by the way, in the beginning, by having phases of the development of what makes science special. It's in all historical disciplines, natural historical disciplines, cultural historical disciplines, and also in recurrent development. So when things have the same sort of lifeline, and of course you know that from astronomy, we know these particular developmental patterns for stars, galaxy, and of course for the cosmos as a whole, and we periodize it and find different phases there. Another important means to increase the systematicity of descriptions is quantification of descriptive statements. You get a higher accuracy of the single statements, and you have more order. So for instance, instead of having, say, qualitatively 20 or 30, perhaps 40 expressions in a natural language, we have a very cheap thermometer, and that gives you 500 distinctions of temperature, say between -20 and +30, in steps of a 10th degree, and it's wonderfully ordered. So you see that these means all increase the systematicity of descriptions, and that is it's a mark of science. Now, the second dimension, I mentioned it already, is explanations. And of course, it's important that science produces explanations, and the scientific explanations are more systematic, that's the claim. So for instance, explanations by empirical laws, say the law of ideal gas, that explains then changes of the state of a large number of different samples of gas, and therefore you unify all of that in that simple formula and have an explanatory stuff that is unifying. That same holds, of course, if you have the larger, even larger scope explanations with recourse to causal theories. They are strongly unifying, for instance, what you can explain by quantum mechanics or general relativity or whatever. So you have a very, very systematic character of these sorts of explanations. Then we have, of course, and that has increased within the last 50 years tremendously, explanations by models of various kinds. You're, of course, familiar with the lambda CDM model, the lambda cold dark matter model. Sometimes people may call something a theory And in the sciences, it's not quite clear. Sometimes people call something a theory, sometimes they call it an equation, sometimes they call it a model. So the verbiage is not very clear, but it doesn't do any damage in the sciences, so far as I know. Then a large group, again, of explanations in science are reductionist explanations, and they recur to parts of a system and the laws governing their interactions. So for instance, in astrophysics, if you want to know something about a star, you look, what are the molecules, what are the forces, what is happening there, which force is the strongest one, is it gravity, or is it still radiation pressure, and whatnot. And then you can, from the components and the interactions, you can tell what the star is doing, in the best case. In everyday life, we find all these types of explanations as well, but in very rudimentary, primitive form. And in science, they are much more systematic. So this is the thesis of systematicity theory. So now I come to the third dimension that I'm discussing, and that is predictions. Predictions do not apply to all sciences, no, in a wide sense. So for instance, mathematics does not produce predictions because mathematics doesn't feature time. And there are many different ways how predictions are produced in different sciences. So the oldest one and direct one is a direct recourse to deterministic or probabilistic laws or theories. So you do that in astronomy, nuclear physics. So you have a law, and that law allows you to predict certain events. A spectacular example, of course, from astronomy is the discovery of Neptune in 1846. And it was based on a prediction by the excellent French mathematician and astronomer Urbain Le Verrier. And he just observed the irregularities of Uranus' orbit. And then from that, he built the hypothesis that this may be due to a yet unknown planet. And he could then calculate where that planet should be. And in fact, it was discovered there within a half a degree accuracy. Okay. The next thing and most important nowadays is the recourse to models, simulations, time series, and statistics. You find that, again, everywhere in economics, meteorology, material sciences, epidemiology, cosmology, etc. These are the things by which we do make predictions nowadays. And all of these forms of predictions, they are more orderly, more explicit, better controlled than everyday predictions. In a word, they are more systematic than what we do in other areas. Now, the fourth dimension I haven't mentioned yet is the defense of knowledge claims. And what systematicity theory claims is the sciences are in the defense of knowledge claims. And this is why this is the most important dimension, because the reliability of science crucially depends on that defense of knowledge claims. All right. And the reason is that science takes the fallibility of knowledge, the possible falsehood of knowledge, extremely seriously, and it develops systematic procedures for error elimination. That's one way of describing it, at least. So the fallibility of knowledge is taken extremely seriously, and scientists know that we must defend our knowledge claims. All these procedures are, again, strongly domain dependent. It depends where you have a knowledge claim, then it depends on that area and the historical situation, how you can defend the knowledge claim. In the formal sciences, this is, of course, in mathematics, is just proof. So if you're a pure mathematician and you write down something that is supposed to be a theorem, you give a proof or you shut up. In the empirical sciences, of course, we know empirical data play the preeminent role, and they are generated by observation and experiments, and then they are processed. And it's important in particular with respect to the test of theories and models. Why? Because theories and models are speculative in principle. They are just constructs in our mind. And someone very original then finds a certain idea how that could be explanatory, but we got to test that because it could also be nonsense. They are very, very risky, and therefore they have to be tested by means of empirical data. I mean, this is what the string theories, the problem string theorists have today, that they have no empirical data really to test that stuff. And we have also, of course, extensive data analysis, because also data can be faulty. Thomas reminded me of Venus, that recent phosphine stuff. So data can be faulty, and of course, scientists are aware of that. And therefore, also this critical attitude extends to the data. Then another thing that explains why quantification, that many people from outside of science don't really understand why science is so after figures, numbers. Quantification is very important here because quantified statements admit of more serious testing procedures. So we saw it already, we get better descriptions, more accurate descriptions, and we also get more the possibility of more severe testing procedures once we articulate our knowledge claims quantitatively. And these are only two aspects why quantification in mathematics is so important in science. Now, the next dimension I call critical discourse. It's a little different from the other ones because it concerns behavior. It concerns the sociology of science. And that means it concerns the social organization of the production of scientific knowledge. And also there you find systematicity because there are countless social institutions that systematically foster critical discourse in science. So for instance, invited talks and webinars have a discussion period where you question critically what the speaker said. You have conferences, you have refereeing of papers and books, and so on and so on and so on. So scientists are constantly criticizing each other, and this is legitimate. This is not, just spending time for nothing. No, this is absolutely essential. Many of these institutional forms of critical discourse are already practiced in science education because this is how socially the students have to be led to science and to the practice of science. Now, it's very interesting that in astronomy, thanks, Thomas told me yesterday, a specialty of astronomy and astrophysics is this decadal survey. It's even a systematic planning of the next decade of research of the whole community, not only of one institute, but of the whole community. I guess the same happens also, I didn't have the time to check it, in high energy physics. That's probably similar, but I'm not aware of other disciplines where that systematic planning really of the whole community of the activities of the next 10 years is systematically done. All right. So the next dimension is called epistemic connectedness, and also in that respect, concerning epistemic connections, science is more systematic than other fields. Epistemic connectedness denotes all sorts of logical and epistemic relations among parts of science, like logical dependency, confirmation, falsification, generalization, exemplification, contradiction, etc. What this dimension says is that all of science is interconnected. Or in other words, there are no separate knowledge islands. And everything in science is connected. And now I come to a question you may have asked already in sleepless nights. Why is chess theory not a part of science, of mathematics, but Sudoku theory is? And the reason is very simple. If you look at chess theory, it's completely disconnected from the rest of mathematics, but Sudoku theory is not. It's a part of combinatorics. It's very interesting. It's also involved in computer science. Anyway, so here you see epistemic connectedness. It had also other functions, but they're not that important in our context. Now, the next dimension is an ideal of completeness. This is also quite strange because in science we have an ideal of completeness, and I will convince you very quickly by a few examples. It manifested in a principal difference between science and many other kinds of knowledge, namely the strong and steady increase of scientific knowledge. This is culturally very strange, and in other cultures we have very seldom, people really consciously building on an increase of knowledge, and that is something, especially since the 17th century, which is a characteristic of this Western tradition of science. What's the driving force behind that? It's an ideal of completeness regarding the domain in question. Scientists want to know everything about a certain domain. And here are some examples from other fields. An axiomatic system in mathematics have to be complete. I mean, as complete as possible, Gödel. Hi, hello, Gödel. The periodic system of elements. Of course, you want to have all the elements. The fundamental interactions of physics. Is it really 4? Is there a 5th one? The classification of biological species, a complete description of processes from beginning to end, etc., etc., etc. Is the spirit of completeness, which is especially visible in myriads of stunning examples in astronomy, and I give you some and remind you of some. So for instance, the description and classification of all astronomical objects up to a certain magnitude in catalogs. So we have these full sky catalogs. This started already very early, 17th century. These are the 5,000 objects that are visible by the unaided eye. And then telescopes were invented. So in 19th century, we have already 30,000 objects, 20 century, we have already 1 billion objects. And today we have exactly 1,697,991,35 objects with property. That's the Gaia satellite data release 2. And if you wait now for another 33 days until 3rd of December, we'll have plus 100 million objects when the early data release number 3 from Gaia is expected. So these are the numbers we are dealing with. And when I mentioned in the beginning, we're talking in biology or whatever, or chemistry, 100 millions, the astronomer says 100 millions? This is what we get, now in a month or so in addition. All right. And it's more to come. Again, thanks to Thomas, he made me aware of the Rubin Observatory and the increase of catalogued objects by a factor of 10 to 100, which is really interesting because here with this billion objects, we see something like 1% of the stars of our galaxy. And if we increase that by a factor of 10 or 100, well, we are not getting completeness, but we are closing in. All right. So astronomers are just, they just love completeness. All right. In addition, there are, by the way, of course, you're aware of that, many specialized catalogs, for instance, for double stars, variable stars, nearby stars, proper motion, etc., all striving for some kind of completeness. And if you look at Wikipedia's list of astronomical catalogs, it has 20 pages. So there are hundreds and hundreds of such catalogs. Now, it's interesting that this systematic idea of completeness is also realized in the sciences in a very systematic way. It's not pursued at random, but also that realization is done systematically. And this is the systematicity in knowledge generation. And here it's an extremely important aspect of this systematicity of knowledge generation, the systematic search for new or improved data. And you find them in archives of all sorts, observation experiments, etc. And astronomy and astrophysics and cosmology is here extraordinary, systematic in at least 5 different respects. So we can trace the systematicity of knowledge generation in 5 different dimensions, if you wish. And I start with the optical telescopes for visible light. You all know this started some years ago in a development over more than 4 centuries. So when Galileo built his first telescope, it was a refractor of 1.5 centimeters, similar to the one that I built when I was 12. It was, I think, 2 centimeters. And then Galileo surpassed me already very early, had 3.8 centimeters of aperture. And then we have Hevelius some years later, 12 centimeter, but with 45-meter focal length. Very interesting, right? Strange telescope. Then reflectors came, 1668, 3.3 centimeters, primary mirror in the beginning, little later, 15 centimeters. So that's a replica reconstruction of Newton's 1672, and you see it's a Newton refractor with the ocular here and the primary mirror here, and here you could change the focal length. And here's a big one already in 1789, 1.24 meters. Here is a person standing, not very comfortable for the astronomers. Then you have Lord Rosse from 1845, 1.83. It's a huge thing. Here is a guy standing. Right, and this is, of course, nothing against the 20th century, the largest astronomical refractor really used from 1897, 1.1 meter, the aperture, and this is the largest that's ever been built. And as far as I can judge, a larger will never, or probably never been built for mechanical reasons. But then, of course, the big telescopes and the Hale, the reflector, the Dream telescopes. When I had this little telescope with 2 centimeters and I wanted to have a bigger one, but my father refused to give me the Hale. So I was disappointed and did not study astronomy, but physics simply. And of course, now, this is where some of you apparently work, the Paranal, 4 times 8.2 meters. And that is not the end of the story. Here we see a picture of the big telescopes, though the Hale is here, it's a very small baby here, but here the 3 very big babies here, the giant Magellan 29, hopefully be finished, the ELT, also in Chile with a 30 meter, more than 39 meters diameter, and the 30-meter telescope, guess what its diameter is in Hawaii. So these are the big boys coming here. Or girls, I don't know whether they're ladies or not. And this one is, of course, unfortunately, a telescope that's not being built, the 100-meter, overwhelmingly large telescope. Okay, So this was the visible light and the development, systematically increasing the power of the telescopes. Now, when other parts of the electromagnetic spectrum were discovered, we see that the the visible light is only a very, 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 very tiny fraction between 10 to the 20 difference here between radio waves and gamma rays. And the astronomers then discovered all parts of the electromagnetic spectrum and thought we get information about the cosmos also in other parts of the spectrum. So radio astronomy started in the 1930s. Then infrared astronomy seriously from the 1960s on, ultraviolet astronomy from the 1970s on, X-ray astronomy from the 1960s on, gamma ray astronomy from the 1960s on as well. So the largest single dish radio telescope, 500 meters aperture, it's called FAST, or Tianyan. It's in Guizhou in China. It's fully operational since 2020. This is the 500 meter thing. The effective aperture is only 300 meter. It's got an active optics. So you can take a 300 meter diameter here, and then you change it into a parabol mirror, and then if something moves, you move that parabol along the way there. So it's a wonderful thing. 500 meters, the biggest radio telescope. Got operational January 2020. Now we have electromagnetic waves of all sorts, and now astronomers discovered additional observational means, and especially astroparticle physics, the discovery of cosmic rays in the 1910s, with a substantial development from the 1980s. An important part here of cosmic rays is neutrino astronomy from the 1960s on, and the largest detector is the IceCube Neutrino Observatory with an ice volume of 1 cubic kilometer, which is quite a big observatory. And looking by means of cosmic neutrinos into part of the cosmos that are not accessible in any other way. So every time you find a new means to look into the cosmos, you find new stuff. That's the experience of the last 100 years or so. And here's this ice cube. The ice cube is down here. Here is the surface, and then 1,500 meters below starts this ice block. 1 kilometer times 1 kilometer times 1 kilometer, and then you have maximum absorption of non-neutrinos, non-cosmic neutrinos, and then you have, of course, corrected the data and everything, but there you see the cosmic neutrinos you're interested in. And other observational means, of course, one of the most dramatic things, at least for me, gravitational wave astronomy since 2016, and there we can finally observe the mergers of black holes, of neutron stars, and we have even one black hole neutron star merger, which is particularly interesting because this guy here also gives electromagnetic radiation. So we have can triangulate, so to speak, if we find the respective radiation and then have more information about the events that are happening there. We have now 4 detectors are available, and they're of course cooperating. We have a dozen of certified events of that kind here, and here's one of the detectors, the LIGO in Livingston, and the arms here are 4 kilometers long, and you then discover along these arms a length difference is about a hundredth of the diameter of the proton. So this is really high tech. This is really high tech. 10 to the minus 22 or something is the relative accuracy. That is incredible what physicists are doing here. Okay, so we had now most of the things I talked about were Earth-based telescopes, but then the extension to space. It's extremely important. One could talk for hours and hours and hours about that. We have now something like 110 space telescopes of various sorts. We have 85 manned or unmanned landings or hard impacts on planets, satellites, asteroids, and comets, partly with sample returns since '59. And of course, not only the astronomers are interested, but also the geologists and the planetologists and so on. So it's extremely thrilling what's happening there. Then we have publicly unknown military missions. Unfortunately, their knowledge is gained that we don't have in the civil areas of science is not accessible to us. It would be marvelous to have that, because I know from the construction of the Hubble telescope, that the military had already constructed a similar telescope and knew much about it. So the military must know much more. On the back of the moon, they're certainly also interested, not only because of the cosmic microwave background. And there's more to come. And finally, is not only these different means, but also the use of these means in systematic surveys primarily. And here I give you an example, especially one example. It's common in astronomy since antiquity in order to accomplish completeness of a certain kind. You know, remember the other dimension, and it's often really gigantic projects. And some of you were involved in this one. The dramatic recent example is the full sky cosmic microwave background radiation, and you measure temperatures there of 2.725 plus minus 2 millikelvin. And that's relevant, as you know, of the most important properties of the universe. So this is really for cosmologists, the most important stuff that's available. And it started with the Cosmic Background Explorer COBE that was operational between 89 and 93. And it decomposed the sky into 6,000 something pixels. And then it looked into every single pixel, and it discovered the CMB anisotropy, among other things, Nobel 2006, the starting point for cosmology with the precision science. And of course, Professor Peebles was involved in these things. He made the preparations to understand what's going on there on theoretical grounds. Now, this was the picture of COBE, which was, of course, extremely exciting at the time, but certainly not good enough. So we needed something better, more details of the CMB were desirable, and then the Wilkinson microwave anisotropy probe, the WMAP from 2001 to 2010, and it decomposed the sky into 3 million pixels. So in every single pixel, you measured the temperature and maybe other parameters, and this is the WMAP picture. Then it's much more detailed, of course, but it's still not good enough. We want to know more, and therefore, again, a systematic development, the Planck satellite. And we have more than 10 to the 9 pixels, so 1 billion pixels. And the picture is this one, the very famous one. It's much more detailed. So if you compare these pictures and this systematic increase, it's this one, the COBE. And I think the angular resolution was something like 7 degrees. The WMAP, the angular resolution was 0.7 degrees. And the Planck resolution was 4 times better, something like 10 arc minutes. And you see the hell of a difference here. And we know much more about the cosmos when we know this one instead of just knowing this one. Okay. So there are other aspects of knowledge generation, not only the systematic production of new data and improved data. So for instance, one can describe that summarily, the systematic closing of knowledge gaps on the basis of existing knowledge. So you can describe the process of science as an autocatalytic or self-amplifying process. When you produce new knowledge, you do not use a scientific method abstractly, but you look what you have and then you start from there. So it's a autocatalytic, self-amplifying process. And if you have enough resources, that results, of course, in an exponential growth. This is what we've seen in many times in the sciences. Then we have the exploitations of other domains of knowledge, very important, especially of technology, including, of course, information technology. And again, in optical astronomy, for instance, just one line, you started all with visual observation, then came photographic plates from 1830s on, with the immense advantage of being able to aggregate, to summarize light, and not only just the second you're looking into the telescope. And then came digital images, again increasing that, the CCD from the 1970s on. And it was an extreme refinement of telescope technology. And the new telescope now, the Rubin, is the biggest and best electronic camera ever being built. So these are the things how knowledge is increased. And now the last aspect where science is more systematic than other forms of knowledge is the representation of knowledge, in which science is just amazing. In the formal sciences, again, we have the axiomatic representation. You write down your axioms, and there, in principle, all the knowledge about your area is contained. And then there are very, very special forms of representation. For instance, in astronomy, you have a nomenclature in catalog. So you have the Messier catalog, the old one, and there you find an object M31, for instance. And then you have the new general catalog from 1888, and that was increased then also. And there you have NGC 224, and that's the Andromeda Nebula, and so on. There are graphs and maps and tables. So for instance, one important representation means there has the Russell diagram, in which you, within one diagram, you see so many things about the development of stars and the main line and so on, and those funny guys who are not sitting there. So Also, there's an additional aspect that this systematic representation increases the efficiency of knowledge reception, and it supports the error elimination and the diagnosis of knowledge gaps. So we have a positive feedback between different aspects of systematicity. So all that systematicity stuff has, again, this positive feedback feature that I claim characterizes science. All right, now let me go to a quick comparison with other positions. And I do that very quickly. I mean, again, I could start with Aristotle and Kant and whatnot, but I only take the most important ones. And there's an idea behind this comparison, namely the heuristic thesis that the earlier answers, what makes science special, the earlier explications of science, they were not mistaken, but they were one-sided. And why? Mostly due to the lesser developed science. I mean, the science at the time of Aristotle was a very narrow little thing. Even the science at Newton's time was a very narrow thing in comparison to what we have today. And therefore, the theories about science were more narrow and from today's point of view, one-sided. And we can correct that today. So for instance, Descartes and other philosopher-scientists, Descartes was a scientist and philosophers, Newton, Galileo, Boyle, these were the heroes there in the 17th century who invented the science and also invented modern philosophy of science. They had the idea that science is special because of the scientific method. I told you about the second phase earlier. And Descartes is extremely explicit about it. These are rules that must be strictly followed. And the strict following of these methods was what makes science special. Now, systematicity, as we don't believe in the existence of these scientific methods anymore, systematicity is more general than that, in that everything that's methodical is also systematic. So everything that Galileo, Descartes, and so on, they are saying, I can say, yes, that's systematic, that's wonderful. But not everything systematic is also methodical. If you have a certain pattern, that's not methodical, but it's systematic. So you see that systematicity, this position I'm developing here, that systematicity theory is more general, and that makes sense given that these earlier philosophers and scientists weren't just stupid. They were doing the best they could given that the material that they had. And we are now further developed both regarding science, further developed also regarding philosophy of science, and therefore we need a more general theory. And my claim is that systematicity theory is the best on the market at the moment. That may change. Okay. Now here's my summary. I had to answer the question, what makes science special? Here is my answer. In comparison to other knowledge-generating enterprises, science is immensely more systematic in various dimensions. And I demonstrated that here in this talk only, well, mainly for astronomy. In my book, I demonstrated for all kinds of sciences and also humanities and engineering science and much, much more. So the pattern that is extremely nicely exemplified in astronomy is that in these 9 dimensions, if you compare scientific knowledge and practices with the corresponding practices, say in everyday or professional practices, it's just that science is much more systematic. Now, the question is that a good thing? It makes science special, but does it do it in a good way? And there the question is, why is science so reliable? That's my second question. And here the answer is, because this sort of systematicity, or this systematicity, extends in particular to the defense of knowledge claims. So especially knowledge claims have to be defended very, very systematically. And that makes scientific knowledge the best knowledge attainable in a certain historical situation by human beings. So it's very important to see that systematicity is what scientists today and at earlier times, they use that to make science as good as possible, as good as reachable. It is all transitory because science developed, but this is the best knowledge we have. And this is why it is so reliable, because in many cases, this control, this error control, goes so far that the resulting science is really very reliable. Okay, and a last look at the literature. And unfortunately, I have to do some PR here. This is the book Systematicity. There you find many other examples. You do not find that many astronomy examples. I developed them for this talk, and second edition 2016. And I thank you very much.
Thank you very much, Paul. This was a wonderful overview. very powerful and inspirational to our astronomer brains. I would like to ask the first question inspired by various Q&A comments by Matthias Wagner and Cristobal Moya. So the systematicity concept relies heavily, like the nature of a scientist and our world, on the concept of causality, of course. But nowadays, what we are pushing, especially the astronomers, is artificial intelligence in our endeavor, right? And so the neural networks get so deep these days that we basically lose the grasp on what the causal connections are in our progress of knowledge creation. So how do you see this progress affecting the systematicity framework, let's say, of how science is special?
Well, this is a wonderful example, because it is not true that systematicity is tied in any sense to causality. This is something independent. It's not part of systematicity theory. I do have in my book a chapter in which I say, once you want to know causal relations, then the scientists go about it in a very systematic way. And there are various systematic techniques, you know, with, for instance, what we see now in epidemiology. So if you want to find out, or also in medicine, when you test pharmaceutica, so you have a control group and you have the original group, and then you have the intervention, and then you have the group with no intervention. And if the groups are statistically the same, then you can say the difference between the two groups is due to the intervention. So we have various means, and this is, by the way, why experiments are so fundamental for natural science. And you poor astronomers, you don't have them. So you have to steal all the causal knowledge from physics and those people who generate causal knowledge. Anyway, but you live good with it. Anyway, so the point is systematicity is independent. So what you see here is possibly similar when you do research on in artificial intelligence, where you now try to find certain regularities, and you can't trace the singular events, but you just have your data, and then you train your data, find the regularities. This is very similar, like the discovery of phenomenological laws in the 17th century. You did not understand what was going on. So the Hubble's law is just a phenomenological thing, but you don't understand it if you just write it down. You just make empirical research. First you sort out the galaxy, you got to have the right classification, then you find it out, and then of course, the law of thermodynamics. I mean, you don't understand them within thermodynamics itself. So what you have to do then later is somehow in science try to understand it. So there may be situations coming up now in science in this ongoing process that we will have a very hard time then to understand the causalities that a artificial intelligence program, or methodology, may discover. We may not understand what's going on because that methodology doesn't give us the causes. It just tells us, it develops like that and you have this and that pattern. But that's, as I said, in the beginning of thermodynamics, people did not understand these laws. It was impossible to understand. Why does entropy increase? I mean, why can we only make experimental changes that increase entropy? This was completely not understandable, only with the advent of statistical mechanics. So this is not a very, so to speak, an extraordinary situation. It's a situation now, of course, it's different from the question of the discovery of phenomenological laws, but it's not something where we could say, oh, this is completely different. No, it's a new situation, and scientists tend to be opportunistic. Wherever you get new insights, you try to get them. And then you say, oh, if I don't understand it, well, perhaps I understand it later. But now I can do something. And these chances are always taken by science. It's extremely opportunistic, where you have a cost-benefit analysis, and then you do where you get most for what you invest in, what you can.
So you would say that this AI business is basically like a fringe tool of the coherentist Johann Queen people that
no, not fringe.
Basically a wider rim of our coherence, let's say.
It's one of these many approaches people try to do. So when you are a scientist and you know much about artificial intelligence, you say, damn it, why can't I use it? If you're an experimentalist and don't know much about it, you say, no, I do an experimental approach. So different talents also add up then. And the basic idea is this freedom within science, that whatever is cognitively justified that you know, or at least plausible, not utterly implausible, you can try it out, right? Once you have tenure, of course. If you don't have tenure, don't do the most risky things. But if you have tenure, you can do it. And this is what happens. And then that may produce results that may provoke more questions than answers. But this is how science works. So it's not fringe. It may not be the mainstream at the moment. It is not. But let's see what's happening in 50 to 100 years. Perhaps it's becoming mainstream. I don't know.
Thank you.
Let's go to Rohan next. But before we continue, Paul, can you stop sharing your screen so we can see all the panel members?
Yes.
Right.
Better?
Okay, Rohan.
Thank you for a very thought-provoking talk. I have a question by Alejandro Clociati. He says that the French philosopher Michel Foucault was particularly critical of classification and showing that they were grounded on a preconceived worldview. So how do we know that the ways we classify in science do not prevent us from generating knowledge in dimension towards which we are culturally blind? What are your thoughts on regarding Foucault's criticism?
Well, first of all, Foucault, as far as I know, was referring to the human sciences. So when we talk about, especially in psychiatric diagnosis and stuff like that, and there, of course, our prejudices, because of our human interests, creep in much, much easier. So in the case of the natural sciences, where we deal with stuff that's so foreign to us, you know, like galaxies or stars and so on, I think the psychological danger of preconceived classification is not that strong. The main thing is that I mentioned only the one direction, namely the classification is the precondition to find good laws, right? But it also works the other way around. You can say, if I have a classification that doesn't lead to any regularities, it may be that the classification isn't okay because it comes from my preconditions and my prejudices. I give you the example, before it was known in the 17th century what the exact difference is between chemical reactions and physical mixtures. There was no way to understand the law of constant proportions, which is the absolute fundament of chemical reactions. So once you found, you make a certain distinction and say, oh, these are not like this solution, so of sugar in water. That was first not seen as different from chemical reactions. But once you see that, wow, that's different because it does not support this law of constant proportions, you can, connect that back and say, okay, those classifications that lead to interesting yet unknown or hitherto unknown empirical laws, they're probably good. So we do have control over them, which is, of course, very different in the human sciences. You know, when all that about the criminal, and this is, of course, in Foucault's work, very prominent, the question of the criminal system, the law system, and that's all connected then with political interests and traditions and Christian faith and whatnot, and other sorts of faith. So it's very, very hard there to have hard and fast distinctions and hard classifications. You also see that in biology, that the biologists are really quarreling really about the fundamental principles of classification of species, because it's artificial anyway, because it's a historical process, right? And the historical process doesn't work in boxes, but we need the boxes. And therefore we have to cut a continuous process and then the result there, and then we have tools and gimmicks, but it doesn't work 100%. So it's a difficult thing, classification, but it's not that we're completely helpless. As Foucault possibly describes it. I don't know that aspect of Foucault well enough, but it's certainly more difficult in the social sciences, in the humanities, than it is in the natural sciences. And as I said, if we've got a classification that leads to new and unexpected empirical laws, then you usually trust the classification.
Okay, let's go to Ivo next.
Yeah, well, thanks, Paul, for this wonderful talk. I have maybe a provocative question, but okay, science is special because of its systematicity. So then, but you assume there are other forms of knowledge which are not systematic. So
less systematic.
Okay, so but can we get knowledge without, with less systematic methods?
What, for instance, your knowledge about where do you live in Santiago?
Yeah.
Yes. So you know something about Santiago. You're not a geographer. Okay. You know something about Santiago, and the knowledge you have is everyday knowledge about Santiago. You know how to get from your home to the university and which train to take to the observatory or whatnot. So you have some sort of knowledge about Santiago. And it's certainly not entirely unsystematic, because you can combine that and say, if someone says you've got to go there, and then you say, oh, okay, I take this one, that one, that one. So you've got some sort of map. But if you compare that with the knowledge of geographers, professional city, town geographers, they have a very systematic knowledge about Santiago, right? So your knowledge isn't entirely unsystematic. It's just as systematic as you need it. Right? And you defend it only and you believe it if your friend tells you, well, after that street, there's the next street, take it, you just believe him. You don't think he's lying to you. So we have techniques of getting around and having everyday knowledge. So for instance, in geographical orientation, and when you compare that to what the geographers are doing, they want to have, the geographers, by the way, have the same as you astronomers. I mean, they all want to know everything. Therefore, they have this geographic information system, GIS, in which they then, United States has 2 billion, well, I don't remember last time I looked at it, 2.5 million, I think, items, geographical items. The planetologists do the same now. They count the items, right? And they do it systematically. So in everyday life, you don't need that. So for you living in Santiago, visiting your parents and bringing your kids to school or whatever you do, or buy a glass of wine, for instance, good Chilean wine. Well, let's not change the subject. Then you know where to go, and it's less systematic. It's not unsystematic.
I don't know if I'm allowed to ask a second question, which is about.
You're very quiet, Ivo. We can't hear you.
Sorry, can you hear me now? Yeah, a little.
A bit better, yeah.
Okay, I'll speak closer to the microphone. The other part of the systematicity is the systematicity of presentation, graphs, tables, and so forth, which improves reception, as you said. But that's true within the scientific circles, I would say. But if you move outside to the society at large, does it work, or do we need a better education or ways that people can interpret what the scientists try to communicate?
Yeah, you are right, but that is not part of my topic. My question was, what makes scientific knowledge special, and how does scientific knowledge grow, in which way? And that is, of course, necessary for the communication among scientists is the important part. So Thomas Kuhn has observed quite rightly that the sciences are quite isolated from society. And scientists typically, I mean, they need the money, of course, but typically they're not interested what the larger society thinks about their subject. They think we know, we are the authority concerning our astronomical knowledge, and whether people don't believe that, well, we can't change it. So the point is here really the concentration on the inner scientific and the working of science. And you are absolutely right. This isolation, and especially these special forms of representation, isolate science even more from the rest of the world. People don't understand. I mean, if you open a book, say, I don't know whether you are also a mathematician, if you take the latest journal of the, I don't know, Chilean Journal of Mathematics, you probably don't understand a word, right, if you're not working in this area. So they have the specialized discourse. That's the price. In order to make progress, you move away from the rest of society. This has been since antiquity. I mean, this is also in theology. It's also in philosophy. It's everywhere. I mean, if you are not a professional, say, tennis player, you don't understand what these guys are talking when they talk about that stuff. It's all specialization, develops own forms of representation and communication, and then the outsiders say, I don't know what they're talking about. So that's quite a normal process. It may be nice, it may be bad, but that happens. And of course, you're absolutely right in pointing. This makes the communication problems for us when we communicate with the public. This is why you have the golden webinars, right?
Okay, let's go to Barbara next.
Okay. Thank you, Paul, for the talk. It was very interesting. I was thinking it was very related to what you were talking just now. if we open science reliability to a wider audience, I mean, we non-scientists often think science deals with very complex issues, very complex problems, and that gives science some reliability. But what do you think of simplicity? I mean, what do you think that making the questions of science simple for us non-scientists get to understand what you're talking about, even though the answers might be complex? I guess what my question is like, do you think there is a relationship, some sort of approach between simplicity and the systematicity you were talking about?
Yes, of course, because simpler stuff can be more systematic, doesn't have to be. But first of all, I think that the axis between simplicity and complexity is perpendicular to the question of reliability or unreliability. So there may be very simple laws that are very, very reliable, and you may have very complicated hypotheses which are completely unreliable. So that's not the point. The question is also complexity versus simplicity is, I think, probably not the best way to describe the problems in science communication, because you can also, complex stuff can be comparatively simply explained if you are really if you're mastering that stuff, because then you know what are the 5 fundamental elements that I got to tell my audience. And then I tell them, well, I simplify a little, but if you understand these 5 points, look, that's the most important stuff. So the complexity, simply, that's not the problem. The problem is rather the specialized language, you know, the special terms that are developed in science. And they are not developed just for fun. They are developed because scientists deal with phenomena we are not confronted with in everyday life. And to describe these phenomena, our normal language just doesn't suffice. We need this specialized language. So if you look at mathematics and you talk about simple groups, for instance, well, you don't know what they are talking about, because if you've never consciously seen the object they are talking about, right, in normal life. And the same holds, of course, now when you go to the cosmos. I mean, if you walk around in Santiago, are you also from Santiago? Yeah, so if you walk around in Santiago, you never stumble upon a black hole or a merger of 2 black holes, right? So the terminology to describe what black holes are doing is just not present in the everyday language. So it's the question of these language gaps. And they are not, you know, on purpose, at least not in the natural sciences. In the humanities, sometimes one gets the impression that people inventing complicated language in order to, you know, make themselves different. So Foucault would be here, perhaps an example, you know, that they distinguish themselves from normal people. But if you look in the sciences and in engineering or so, these people are so sober. They don't use this baggage, you know, of complicated language. They want to be as simple as, because science is so difficult. You don't have the time to spend additional time on inventing complicated, unnecessary jargon. You don't do that. On the contrary, sometimes scientists are quite sloppy concerning certain, as I said, with hypotheses, theories, and models, and scientists just don't give a damn whether there's a difference. It doesn't hurt the science. For philosophers, it's difficult because they don't understand what the others are talking about. But that's, again, this language gap. The language gap is much more important than this dimension of complexity and simplicity. And again, this is independent of the question of reliability and unreliability.
Thank you.
Did I answer your question a little, at least?
Yeah, you did. Thank you.
Great, thank you.
Okay, I have a question from the Q&A. So Enrique Paillas has said, are we lacking in terms of the teaching of philosophy to our new generation of scientists? I mean, the very term PhD comes from Philosophiae Doctor, so that's the Latin, so Doctor of Philosophy. But this discipline is often missing in most science undergraduate or graduate programs, at least in Chile. Is this a problem, or can we do fine without it?
Well, this is a complicated question. I mean, there are many, say, physicists, there are no investor mathematicians who think that philosophy is absolutely useless. You don't need it. It doesn't help you. So if you ask, for instance, Steven Weinberg, also a novelist, and he said, I know the history of physics from 1945 on. there was not a single instance in which philosophy contributed in any positive sense whatsoever. So in order to learn technically, to learn physics or chemistry or biology or astronomy, you don't need philosophies, no doubt. The question is, when it comes to the larger questions about science, if you want to understand what's, in another talk, I said the question, what's the epistemic status of physics? So what is the quality of the knowledge that physics produces? If you come to these questions, and also people like Stephen Hawking or Roger Penrose, again a novelist, they were discussing that, and they couldn't find an agreement. And they asked the question, I mean, what is physical knowledge? Is it really knowledge about nature as it is in reality, or are we only producing models, that function somehow? And if you come to these questions, which are unimportant for your day-to-day work in the observatory or in the lab, but once you think about that, then philosophy becomes important. And there are some well-trained people who deal with these questions. So the question is, I mean, what's an university education for? Do we simply produce people who then know their craft? Or do we try to educate people who have a wider horizon, who then are able, to discuss critically, for instance, the value of science, the necessity of science, say in a pandemic or so, who then try to explicate? I mean, isn't this here a wonderful example of what's happening, that you ask the philosopher, and I'm an amateur in astronomy, and I try to explain from my point of view a larger picture of science and how astronomy fits in there. And now it's the question, do you want a university that your students have this larger picture? Or do you think, no, I only need the engineer who builds my observatory, and then I need the astronomer, who uses the refractor, the reflector. So that's the question. That's the question about goals. So why are we doing all of that, all that cultural stuff like astronomy? And there, I would think, and also if you do less cultural, but just, earning money and producing food and stuff like that, I mean, we're doing that in a larger context. And the larger context is culture. And to eat nice food is good, but nice food is not all in life, in human life. And I think culture, and I defend, of course, science very strongly about those people who think, oh, these astronomers, they spend so much money, I want to go to the opera. And I say, look, opera is also part of culture, right? And it's even more expensive, right? It's not democratic. When they say, yeah, so few people are only interested in astronomy, I say, how many people are interested in the opera? Every seat is 100 euro per seat. So it's part of culture. And so I defend that. And if a university then has an education, say for scientists, astronomers, where people should not only know of this part of culture, but also how it's embedded in a larger picture, including philosophical questions, the philosophical meaning questions about on the basic level. I mean, what sort of knowledge does science produce, right? Is it different from other forms of knowledge and such stuff? Then you want to have philosophy. I mean, if you look at a country like Norway, they still have this, as far as I know, they still have this old tradition that the first semester for everyone is philosophy, a full semester. Therefore, Norway has 60 philosophy professors, because all these in University of Oslo, they have 20,000 students, and all the students have one term of philosophy, just getting this broader background. Whether that does the Norwegian economy good, or whether these are better people or whatever, I don't know. I can only say, and I'm not trying to sell it, I'm only saying I'm very happy when people ask me, tell us something about philosophy that may interest us, like in this situation. I'm not going to sell it because the image of philosophy is much too bad. For good reasons, by the way, unfortunately.
Very interesting, thank you. We're going to have 2 more questions. So let's go to Dietrich next.
Yeah, thank you. I would like to start with a question from the Q&A session by Ingrid Bravo. And she said, systematicity is the golden egg of the 17th century. But in 2020, the value of trust in data is the issue that we need to resolve. How can we do that? And if I generalize that question, I understand it correctly, the question is, can and should we trust science? I would think and say, yes, absolutely. And a few years ago, I was one of the co-organizers of the March for Science here in Munich. And of course, there were the usual suspects who were very critical about science. And there was in particular one person who lectured us on all the fallacies of science, starting with the geocentric picture of the world. And then I asked him, well, who has corrected all these mistakes? Have these mistakes been corrected by scientists or by other people? And then he was fair. He said, well, yeah, there you have a point. It was done by scientists. So I would argue that the thing that distinguishes science from many other disciplines of human thinking is that science is self-healing. If someone says something wrong, it will not go unnoticed forever, and it will be corrected. It may take a century, but it will be corrected.
Yes.
And there are very other areas of human life that have the same property. Would you agree with that?
Yes, I would agree there. First of all, systematicity is not a concept from the 17th century. It came later, really. I mean, the idea of a system, that's now getting a little complicated, because systematicity, although the word is derived apparently from the noun system, the adjective systematic and more systematic is much wider. So a system is really something built by certain blocks, and then typically as an axiomatic system, then you know exactly what you're talking about. So the meaning of system is really axiomatic system. And I'm going beyond, much beyond axiomatic systems. Axiomatic systems are a particular case of systematicity. And by the way, this was already seen in the 18th century. So one of the D'Alembert, the great mathematician, he said, you know, thinking in terms of systems is philosophy, and thinking systematically, that's science, right? So this is also my line. Now, the trust in data, well, I mean, yes, the data we are producing are not just like, you know, directly looking into something and seeing that. So if I look at the data, I don't know enough about the data production in astronomy, but I know a little about in high energy physics. I mean, when you have, when the detector then throws away 10 to the 9 events, and one is only kept because the events are by the algorithm determined to be unimportant, then the data are, of course, already highly theoretical. And this is absolutely right. This is also the great, in a sense, great progress of science since the especially 19th century, that it's more than just looking at things and then trying to generalize inductively, but that we have highly theoretical data that are highly theoretical loaded. And of course, this load of theory is always also a possible import of error. So trust in data, no, data analysis, right? Critical data analysis will become more and more and more important, right? And of course, only the specialists will understand and be able to judge whether it's good enough or not. And there you are right. There is this sort of self-healing, this self-correction, and this is due to dimension 4, is that this deep entrusted tendency to error elimination. And scientists are aware of the errors. I would not say, by the way, that the heliocentric, the geocentric system was a mistake. That's not a correct description. It is false, but not a mistake, because a mistake presupposes that someone committed a mistake. But that was by far the best theory you could come up with during the time before Copernicus. It was really by far the best theory. And if you look at Aristotelian physics, which I did, which sounds very strange to us today, this is a fantastic theory. He was a fantastic theoretical physicist, Aristotle, and he just, on the basis of the data he had, he just did the very best he could. Why did people believe in the finality of classical mechanics during the 19th century? Well, there was no indication that it couldn't be, it shouldn't be ultimate, right? So in retrospect, we can say, whoops, they were wrong, but they didn't commit mistakes. This was good science, it was the best one could. And then, as you say, then, you know, doubts came up. And these doubts then amplified, and in a functioning science, these doubts are not suppressed, but they may have for some time a hard time. You know, you find that also in the 20th century physics, if you look at the, for instance, nuclear physics, the authority of Bohr kept the liquid drop model of the nucleus longer alive than was justified. But it was just a delay of 5 or 10 years. And that's the sort of thing that we get due to dogmatism, some sort of delays. But once there are data, and as long as, especially also this fifth dimension, the sixth dimension, the critical discourse, if the institutions are correct, if they are not suppressed politically or by power elites within the science, if that works, then it's the best institution we have. We human beings did not come up with anything better. We don't have an alternative, right? It's just the very best. And we got to be vigilant all the time. And most scientists are, because there's a premium, of killing a reigning theory. Not immediately, but in the longer run, you'll be the big guy, right? Criticizing the establishment. And big lady, by the way. All right. Did I answer the question?
Okay. Let's go to Miguel then for our final question.
I have the honor of bringing up the final question. I find it very interesting. Eric Baranzuela asks, how do scientific breakthroughs happen? I have my own answer, which is down to earth and has to do with research funds. But probably we would like to hear your answer as the end point of a wonderful talk.
Thank you. Yes, that's a very interesting question. And I learned a lot from Thomas Kuhn there, who investigated exactly this question in the history of science. And the typical pattern is that people discover what he calls an anomaly. And an anomaly is where something works or doesn't work, be it theoretically, be it experimentally, observationally, contrary to your expectations. So there is a tension building up, right? And something is just different somehow, unexpectedly different. Now, the point is that happens all the time. And usually scientists, in many cases, then say, yes, I don't know why this apparatus doesn't function or why I don't see that object. I don't know, we'll find out later. So it's quite a tendency not to get too hysterical about that. Because if you follow up all these anomalies that you encounter, you never get anywhere. You're just polishing your apparatus all the time. So you got to be somehow, cavalier, but not too long. And the typical situation is that a certain anomaly then does not only appear in one particular location, not only geographically, but also cognitively, but there are clusters then of anomalies. So what happened, for instance, if you look at the transition from Bohr's atomic model to the quantum mechanics, full quantum mechanics, which happened between 1921 and 1925. Bohr's model was, in the beginning, it was completely rejected for 2 years, until Sommerfeld then started calculating, refining it in 1915. And then for 5-6 years, it was just wonderful. A few things didn't work. So you couldn't calculate helium. You could of course, calculate atoms with 1 electron in the outer shell. Wonderful. But there were certain things you couldn't calculate. And after a while, then nothing could be calculated anymore. You had your wonderful, influence of magnetic forces, electric forces, blah, 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 line splitting and all that stuff. So people thought, this is a wonderful theory, but then it didn't work. And certain problems, the very, very best people tried everything and it didn't work. And because of that anomaly, if the theory had been better, it should have worked, then people said there must be something awfully wrong here, right? And then people started then slowly to talk about alternatives. And then these geniuses like Schrödinger and Heisenberg came up with stuff. So it's anomalies where things don't work. This is where the birthplace of deep innovation. But again, it's a very tricky process because not every anomaly is significant. I heard from people in laser physics, when I studied at Imperial College in 71, when laser was comparatively new, then I met a physicist who told me, I did in my lab, I had the laser reaction. I had this light there and I didn't understand. And apparently it was in 10 labs, people had the laser reaction. And most thought, oh, something is wrong with my machine. And only one really realized, wait a minute, that could be something really significant. This was the laser development. So it's just a normal part, both of theoretical life and experimental life, that things don't work in unexpected ways. So you don't have to be hysterical, but on the other hand, you're going to be alert. Yeah, and the really good physicists are those who have a better hunch, and astronomers and so on, natural scientists, who have the hunch. Look, this is interesting. That's not interesting. So no really systematic answer. This is a historical process, right? It's a historical process, and historical process, they're not driven by some internal absolute systematicity.
There is one, though, and if you look into history, you will see that when humankind improves by a factor of 10 the capability of observing something, and that works for astronomy and also for biology, then discoveries will happen. Yeah, that's not a good argument.
Yeah, but look at high energy physics. I mean, people are really trying to find where does the standard model break down, and they've been looking now for decades. It's the counterexample, right? And people were exactly doing that, increasing accuracy and so on. You only find anomalies if they are there, and you don't know in advance, right? Astronomy is very lucky in that respect. Every time, you increase accuracy or wavelength or whatever, a factor of 10, you find something new and the universe looks completely different, right? And then you add up all the pieces. You are very lucky, right? Well, let's see how long that goes. I mean, physics was very lucky in from 1840 to 1740 1740 to 1890 in the face of classical physics. Everything worked, right? Everything you tried new in acoustics, thermodynamics, would not, fluid dynamics, everything worked with classical physics until it came to an end, right? So yes, as for astronomy, more funds, right? Because factor of 10, and here you go, find something new. But if you go to the high energy physicists with Atlas at the LHC, they're quite frustrated.
Okay, let's wrap up there. So thank you everyone for joining us today for Paul's talk. And thank you very much, Paul, for taking the time to tell us about the philosophy of science. It was very interesting. We'd like to ask all of our audience to fill in the survey that should appear at the end of the Zoom webinar. And our next scheduled talk will be on November the 6th with Alexei Viklinin, a professor at the Harvard-Smithsonian Center for Astrophysics and co-chair of the Science and Technology Division team for the Lynx X-ray Observatory, which is one of the new great observatories. So for now, stay safe, stay healthy, and we'll see you all at the next golden webinar.